Electricity topic 4. This is going to be part A, so we're just really just going to talk about the definition of current and the equation for current, and we're not going to go into the properties of series and parallel circuits. That's something we'll do later on next week. Okay, to explain the concept of charge, I'm going to take you through these amazing drawings that I made, and as you can see, I am very artistically challenged, and probably one of the reasons why none of my friends ever want to play Pictionary with me. However, I'll try my best with these very substandard diagrams here. But the point I'm trying to make here is that charge or current is really the delivery system of energy in the circuit. So we've established what 1 coulomb is. So we know that 1 coulomb is that 6.24 times 10 to the 18 electrons. In a circuit, 1 coulomb is going to be equivalent to 1 amp. So far you've done 1 or 2 labs looking at measuring current, and you would have measured in milliamps or amps. And every time you have 1 amp of measurement, that means that you're looking at 6.24 times 10 to the 18 electrons. And so it is, the electrons are there, and again, the electrons don't move around the circuit like the way we envision them. They're there to provide a medium for the energy to be supplied throughout the circuit. So one way of thinking of it is, if we take 1 coulomb, we can say that, again, that is equivalent to 1 amp. So that would be like saying we have 1 delivery truck. So the delivery truck is the 1 amp or the 1 coulomb. In that delivery truck, we would put energy inside. So we would put in, say, 12 joules of energy. And so when it goes to that load, that light bulb, it's going to drop off 12 joules of energy for that particular light bulb. And so that's going to make it, whatever brightness that you look at, right? But then I decide to, or I change the amount of current in the system. So I can change that by changing the resistance, and I can up it to 2 coulombs of charge. So now I have 2 delivery trucks. Well, each delivery truck is the same size, even though my diagram doesn't look all the same size, but we're making them the same size. So this delivery truck here, delivery truck 1, delivery truck 2, both the same size, both carrying 6.24 times 10 to the 18 electrons, same size load. So then we can put in 12 joules of energy here, 12 joules of energy in the second truck. And once we do that, what happens is the light bulbs actually get brighter. If we measure the light bulbs, it'd still be 12 joules of energy going across, but the volume that's traveling through there is so much more. So you have the ability of dropping more energy off as you increase the current. And this is why they say current kills, because current carries the energy, and so the more current you have, the more energy that you're going to have flowing. Unfortunately, if someone gets electrocuted, the more energy they're going to have flowing through their body. You can have a huge amount of voltage, but a really tiny amount of current. Like you can have a 0.001 amps of current, and that's very little energy delivery systems. Those are tiny trucks that are delivering it, and so they can't deliver as much energy. They only deliver a fraction of the energy to the actual, say, the light bulbs. So in that case, or in this case, sorry, as I increase that current, the brightness of the light is actually increasing. And so every second, I'm actually delivering twice as much energy to the light bulb as opposed to the first delivery truck. And so when we look at the equation, I is charge divided by time. So it's how much charge is passing a given point every second. So the more charge, which means the more current I'm passing through, the more energy I'm actually delivering to the circuit. Even though it may be a very small amount of voltage, it gives me the ability to deliver more. So always think of current as the delivery system. Another way of thinking about it is, those electrons, they are just sitting there and they're excited, they're moving around, they're moving their hands around, they want to pass something through. Sort of like a big mosh pit. And as soon as the the energy is allowed to pass through, they are pushing that energy through, and the more current you have, the bigger the mosh pit you have. The more people you can send through there, and that each person would be X amount of voltage, and the bigger the mosh pit, the more people you can send through. And it's really just how much current is being activated to allow more energy to be delivered to the system. That's really what current is. It's a huge component of the circuit, and you can never, as we go through the unit, we can never separate the idea of current, voltage, and resistance. We'll always talk about those three working together. So going back to the notes, that's what's being discussed in this section. So we have I equals Q over T. So Q is the charge, right, which is indicated here. And I is current. That's the symbol we use in our equation. Remember, when we look at circuits, I in the circuit is equal to amps, right? So when we measure in the circuit, we're going to get 2 amps. That's the number that we'd use for I. And T is time, and time is always measured in seconds. Remember, like I mentioned before, 1 amp is really 1 coulomb per second. So 1 amp is really equivalent to 6.24 times 10 to the 18 electrons. So they go hand in hand. So we talk about amps in a circuit. Amps are really coulombs. A coulomb is 6.24 times 10 to the 18 electrons. So we're really, when we look at current, we're looking at how many coulombs are passing by in a given second. And remember, it's that huge net movement of electrons. As we talked about in class, the ammeter is connected in series. And when it's connected in series, we're monitoring the actual flow of electrons through the circuit. So you're going to, for homework, you're going to be practicing using this equation, I equals Q over delta T. And so you're going to rearrange that equation to find either the standard, the I, which is the current. You're going to have to rearrange it to find the coulombs. And then you're going to have to rearrange it maybe to find the time. Remember, Q is always in coulombs. Remember, T is always in seconds. And I is always in amps. So always convert to amps, coulombs, and seconds in your equation. And that's about it for part A of topic number 4. The other section of topic 4 is really dealing with what's happening right into the circuit, and that's something we'll discuss after we complete a few of our labs.